Anyway, good afternoon. Compared to the previous two talks, this presentation is very low-key. This is just a review of some of the actual results I have gotten at the start of the year. I started working this presentation before the Perseids, so I haven't included any Perseids, but I got some really quite interesting results from that shower. So, a very brief history. I've been interested in spectroscopy simply because of my engineering background forever. And I tried photographic spectroscopy for decades and recorded nothing. However, I moved to video in 2006, and in 2008, I came into a very small 25mm square grating, which I blue tacked to the front of one of my video camera lenses. And that's the picture on the right-hand side. The very first night I tried it, there was a result. I couldn't believe it. And ever since then, I've just tried to chase better and better performance. For me, it's a technical challenge. I'll leave the results to the experts to tell me what it all means. But in the intervening 10 years, I've gone through various WATEC cameras, and a few years back, the ZWO Chinese company released the 174. Now, what is interesting about the 174, it has a global shutter. So it takes one complete frame each time it exposes to build the video up. The WATECs are interline devices, so they scan once and then rescan. And in that time, the Meteor motion can actually introduce various artifacts. And when it came to processing, you'd get spurious lines which just didn't really exist. So this interested me a lot. 2007, I decided to take the plunge and buy one. I've now got 4 of them, so I don't have a globally expanding network, but I do have a garden expanding network. They're scattered around the place. I'm often asked, in fact, frequently asked, how do you attach the grating? So for everybody that asks, it's an empty filter ring with the locking ring removed, plop in the grating, and then use the lens hood to secure the grating in place. And that allows you to rotate the grating so that if you're observing a shower, you can pre-orientate the grating so the dispersion axis is along the line where you think you're going to get the meteor. When it comes to sporadics, it's blind luck. But that's the arrangement there. There's just the camera, lens, a stepper ring, and then the actual grating itself. To get the better resolution, to see more detail, you have to go to a longer focal length lens or a larger sensor, or both. Background image was the Perseids from 2013, 12mm lens, low count grating, and you can see the meteor and the spectrum, all of it from about 370 nanometers to 950. Or it's along here, or you can go longer focal length, higher line count, more recent, and you get a much better view, but you see much less of the spectrum. There's about 40 lines in here alone. But as I say, it's always a compromise. You're trying to balance the optimum to get the best efficiency so that you get the most results for the time spent observing. So the actual results. 2020, the weather is usually horrible in this part of the world, and it was, so I didn't see much of the Geminids. However, a few days after, it's the overlooked shower, the Ursids, much lower ZHR, but they do show occasional outbursts of activity. The weather over the 21-22 this year was fantastic. I mean, beautifully clear. So I had the system out running. I try to have the 2 pairs of cameras such that one will catch the zero order or the meteor, the other will catch the spectrum. The alignment wasn't great, but I did catch this really nice Ursid here, probably about -2, -3. That was on one camera. On the second camera was the spectrum, and it was just perfectly dispersed. So up here we have iron lines about 350 nanometers. We get through more iron lines, magnesium group, ionized calcium, silicon, more iron, lots more iron, magnesium, iron, sodium, more atmosphere, and then out to the infrared atmosphere, 777 oxygen, and so on. So it's the system is actually far superior to the WATECs. That's the integrated composite image of the whole video spectrum, as it were. I do an analysis similar to what Salvatore describes by dividing through by a Vega spectrum to sort of flatten the response of the instrument, and then using previous calibrations, you begin to match up the lines. So this is a sodium line, a magnesium line, ionized silicon, iron, ionized calcium, and so on. You get nice resolution plots like that. This is the sort of synthetic spectrum that you can generate with some of the software that I use. From the very beginning, I've used a Visual Spec by Valérie Denou, and it is just fantastic. And it has all these little built-in features that make really, really appealing graphics. So that was the quadrantids, the ursids. Moving on to the quadrantids, a few years later, excuse me, I had improved the alignment slightly. So got two really nice, again, -2, -3 magnitudes, meteors there. And this time I'm just looking at a single video frame from the global the global shutter. And this, you can see the advantage, you can look at just individual strips of the spectrum. So you can actually do temporal evolution if you're interested in that. And what you can see is, perhaps reassuringly, they are almost identical. The features are all the same, the intensities are all the same. And again, we go from about, I'm not sure if that's a line, that's probably about 350 nanometers. It's right on the cutoff of what a silicon detector can actually detect, running all the way up here to about 950 nanometers. And if you know your quantum mechanics with the band gap, that's about this maximum a detection range you can get from a silicon detector. So they really are quite impressive, the camera's performance. So just using the same sort of method, dividing through, calibrating with known lines, and we see the two graphs there. So the interesting thing is that in 2015, I had got some results, and it looked like the magnesium was just immense, and the quality of the spectrums weren't that good. But again, reassuringly, the magnesium signature of the quadrantids is very, very strong, and they are almost identical, with the exception of that one line there. You can see it in the color versions quite nicely. It's round 431 nanometers, which is ionized silicon. It could be, and it could be another iron line, I'm not sure, but the rest are ostensibly identical. So very, very strong magnesium, both here and in the near ultraviolet. Let's see. Now, this is the interesting one. This was the best one of the winter and spring. Observing the Lyrids, I captured this fireball. This was -4, -5. And I worked very closely with the guys in the nematode group, and these guys get a lot less credit than they deserve. They're a fantastic team. And Alex, I got in touch with Alex Pratt. He sort of coordinates all the observations, and some of the nematode guys had caught this one, and they produced this lovely orbital graphic for me from UFO capture. But the really interesting thing is very, very low geocentric velocity. And when I first saw this, I'm thinking, this is kind of familiar. Where have I seen this before? Because in higher velocity meteors, blue end is here. This is the sodium line. From about this point on, you start to get much greater atmospheric emissions from higher velocity meteors, your oxygen and nitrogen lines, but there's none present here at all. So the very low speed has masked a lot of these features, but also, has revealed these features, but also has revealed very subtle lines in here. And that's what caught my attention, because if you remember, it does look a bit kind of familiar. And that was the spectrum that was sent to me by Ed Majdon in Canada, the unmeasurable mystery spectrum, which I managed to figure out. And it is almost identical to the video one. I mean, right, this little very bright, intense iron line here, there it is there. And I think it's that one there in the second. This is the second order spectrum from this part here. Almost identical. Now, this is just fascinating. So we can say that maybe Ed's was a low velocity meteor as well, because there's no infrared absorption, no infrared emission from the atmosphere. But The really cool thing is when you do the calibration and the little graphic, there are some little extra lines start to appear here. Now, I contacted Jerry Borovichka. He's the go-to guy, an absolute expert. He's done some work on atmospheric emissions, which in higher velocity meteors have a shoulder about here. And this usually comes from nitrogen emissions. And likewise, there's a sort of extension here you see in some spectra. And normally these lines are masked. But I read back through some of his other work, and he put me onto two papers, one by, I'll just make sure I get the names right, Berezhnoi in 2018 and Popov in 2021, brand new work on what they call the orange band problem. And they've been modelling emissions from iron oxide and calcium oxide. And this is a spectrum from the Benizov meteor from 1991, I believe. And they look at other older fireballs as well. And what is intriguing is that if you match up the components of the spectrum, this is the sodium line. Now, there are known calcium, silicon, I think there's silicon, ionized silicon in there as well. I'm looking at the old photo handbook because there's a cracking picture in there of it. But also, without the masking features of the atmosphere, we're tantalizingly close to seeing these other lines, which may be additional oxide lines. Now, whether that's oxides in the meteor or whether it's actual chemistry going on in the atmosphere, I don't know. But we're getting really close to seeing some very, very detailed stuff. And this is now comparable to the highest resolution that were obtained to the 60s and the 70s with 300mm objectives and 30 centimetre by 24 centimetre plates. So the video technology has now got to the stage that it's becoming comparable to that level of detectability if the meteor is slow enough and it reveals its secrets to us. So from my point of view, as just an observer, all I can say is I will keep on observing, keep on collecting spectra, and the true experts can figure out what it all means. So I've sent the paper to Havor for the proceedings, but just in case anybody wants to look it up, those are the two key papers which describe this in a lot more detail. And certainly from my own observations, this is the first time in the 12 years I've seen a spectrum that we can get down to that level of resolution. And I'd certainly like to acknowledge Alec and the guys from Nematode. They've been there fantastic to work with. And another thing I'm often asked is, we've looked for your spectrum, Bill, we can't find them. Most of them go to Tracy in the meteor column notes of the astronomer, and you can look them up there, they're all there. And if anybody wants them, just send me an email. So I think I'm just about on time, a little bit ahead, but thank you for listening.